What specific problem does the concept of synthetic continued pre-training aim to address, particularly in the context of language models and knowledge acquisition from small corpora?
Synthetic continued pre-training aims to address the challenge of knowledge acquisition from small corpora, which is often ineffective due to the limited volume and diversity of text in such datasets. Traditional continued pre-training struggles to teach language models the knowledge contained in small condensed corpora, as evidenced by the failure to generalize from a small set of documents. To overcome this, the proposed method synthesizes a larger, more diverse corpus from the small dataset, enabling the model to learn effectively. Specifically, the EntiGraph algorithm generates diverse representations of knowledge by creating a knowledge graph from the source documents, which enhances the model's ability to acquire parametric knowledge. This approach is crucial as it allows language models to adapt to specialized domains where only limited textual data is available, thus improving their performance on knowledge-intensive tasks.
How does the EntiGraph algorithm work? Illustrate the process step by step, including how entities are extracted and how relationships among those entities are analyzed to generate synthetic knowledge.
The EntiGraph algorithm operates through a three-step process to generate synthetic knowledge from a small corpus. First, it extracts a list of salient entities from each document using an entity extraction prompt directed at a language model, which identifies key concepts relevant to the text. Next, for each extracted entity, the algorithm generates a synthetic document that describes the entity in the context of the source document, utilizing an entity description prompt to provide detailed information about the entity's role. Finally, the algorithm analyzes the relationships among subsets of the extracted entities by applying a relation analysis prompt, which generates synthetic documents that describe how these entities are interconnected. This hierarchical prompting strategy allows EntiGraph to create a diverse synthetic corpus that enhances the model's ability to learn from the original condensed knowledge in the small corpus.
Can you provide a simple illustrative example of how EntiGraph generates synthetic data from a small corpus? Walk through the main steps using a specific subject matter, such as linear algebra.
EntiGraph generates synthetic data from a small corpus, such as a linear algebra textbook, through a three-step process. First, it extracts salient entities from the document, for example, identifying terms like linear space, vector, and SVD. Next, for each extracted entity, EntiGraph generates a detailed description contextualized within the source document, such as explaining that a linear space is a set satisfying specific algebraic rules. Finally, it analyzes the relationships among subsets of these entities, producing synthetic documents that describe how entities like linear space and vector interact in the context of linear algebra. This hierarchical prompting strategy allows EntiGraph to create a diverse synthetic corpus that enhances the model's ability to learn from the original small corpus effectively.
What key theoretical or practical benefits does synthetic continued pre-training with EntiGraph offer, compared to traditional methods of knowledge acquisition from small datasets?
Synthetic continued pre-training with EntiGraph offers significant theoretical and practical benefits over traditional methods of knowledge acquisition from small datasets. Firstly, it effectively addresses the limitations of simple continued pre-training, which struggles to learn from highly condensed and less diverse small corpora, as evidenced by the failure of models to generalize from limited data. By generating a larger, diverse synthetic corpus through the EntiGraph algorithm, it enables the model to acquire parametric knowledge more effectively, achieving a log-linear scaling trend in accuracy as the synthetic token count increases. Empirically, the approach demonstrated that continued pre-training on the EntiGraph corpus resulted in a substantial accuracy improvement, from 39.49% to 56.42% compared to traditional methods, which plateaued at lower performance levels. Additionally, the knowledge gained through synthetic continued pre-training is complementary to retrieval augmented generation (RAG), indicating that it enhances the model's performance in knowledge-intensive tasks without requiring access to the original source documents during inference. Overall, EntiGraph's hierarchical prompting strategy fosters diversity in knowledge representation, which is crucial for effective learning from small datasets.
How was the effectiveness of the proposed method validated? Describe the experimental design, datasets, benchmarks, and metrics used to assess the enhancements made by the synthetic continued pre-training approach.
The effectiveness of the proposed synthetic continued pre-training method, utilizing the EntiGraph algorithm, was validated through a series of experiments involving a specific dataset and evaluation metrics. The experimental design involved using the quality dataset, which consists of 265 articles and short books totaling 1.3 million tokens, and generating 600 million synthetic tokens through EntiGraph. The model's performance was assessed using unambiguous test queries, QT, derived from the dataset, which included 4,609 multiple-choice questions designed to probe the model's acquired knowledge without access to the source documents. The primary metric for evaluation was the accuracy of the model in answering these queries, with results showing that the model's accuracy improved from 49% to 42% after continued pre-training on the synthetic corpus, demonstrating a log linear scaling trend with the number of synthetic tokens. Additionally, the model's performance was compared against baselines, including continued pre-training on the raw corpus and a rephrased corpus, highlighting that the EntiGraph approach significantly outperformed these alternatives.
What notable results were achieved following the implementation of the EntiGraph method, particularly regarding QA accuracy on the quality dataset? What implications do these results have for future applications of this approach?
Following the implementation of the EntiGraph method, notable results included an increase in closed-book QA accuracy from 49% for the base Llama 3.8b model to 42% after continued pre-training on the 600M token synthetic corpus generated by EntiGraph. This demonstrates a log linear scaling trend in accuracy as the number of synthetic tokens increased, with the model achieving 80% of the accuracy improvement that would be expected if the source documents were available at inference time. The results indicate that synthetic continued pre-training effectively enables language models to acquire knowledge from small, specialized corpora, making it a viable approach for domains where data is limited. Furthermore, the findings suggest that the knowledge gained through this method is complementary to retrieval-augmented generation, RAG, indicating potential for enhanced performance in knowledge-intensive tasks. This positions the EntiGraph method as a promising strategy for future applications in specialized domains, where traditional data acquisition methods may fall short.